Hello everyone, my name is Caroline and I'm currently a PhD student in bioinformatics in the Lamuse lab at ARIC. And today I'll be discussing how metric inference from dose response data can assist us in compound selection. The current work is done in the context of the drug discovery process, and it is based on our previously published methodology where we define a Bayesian model to analyze dose response data. Rather than obtaining single-point estimated values of each of the log logistic parameters, we infer the posterior distribution, allowing us to establish confidence interval bounds and to account for the inherent experimental and analytical noise. We also propose a methodology to statistically compare the metric of two dose response curves. We are now interested in extending the use of this posterior distribution to assist us when selecting compound. In order to do this, we first want to account for uncertainty when ranking compounds based on a single metric, and secondly, we want to incorporate the notion of statistical significance when comparing more than two compounds. To demonstrate our proposed methodologies, we use an in-house test dataset with 22 compounds. Compound X here is our landmark compound, and all responses have been normalized to represent cell growth inhibition rate. Using predefined prior distribution and our Bayesian model, we inferred the metric posterior distribution of all 22 compounds. For simplicity, we will only consider the IC50 and max response metrics, but keep in mind that any other metric could be considered. It is common practice during compound selection to ask what are the M-best compound, with the definition of best being relative to the metric considered. Metrics values are ordered accordingly, and a list of the M-first compound is returned. This is what figure 3 represents. The top panel, we have the top 5 compound with the smallest IC50, and in the lower panel, we have the top 5 compound with the highest maximal response. This approach does not account for the uncertainty resulting from the entire analytic pipeline applied to the already noisy raw data. So we propose to assess rank probabilities for each compound using the inferred posterior distributions. Our initial question now becomes, which compound had the highest probability to be among the M-best? To answer it, we compute the probability that a compound C is at a given rank R for a specific metric. And from these probabilities, we obtain a distribution of rank for each of our N compounds. And this is what is represented in figure 4 by the heat maps. On the left, we have the IC50 ranks, and on the right, we have the max response ranks, which seems less certain than the IC50 ranking. Given the rank probabilities, we can identify compounds that have a probability of at least P of being in the M first ranks. Back to figure 4, we identified 7 compounds that have a probability of at least 1% of being in the first 5 ranks. The posterior distribution are indeed on the far left compared to the other compound. We did identify the 5 compounds of figure 3, but we also identified analog 21 and 10. Analogs 14, 21, and 10 seems to have very similar posterior. It would thus seem incorrect to conclude that analog 14 is amongst the top 5, while analogs 21 and 10 are not, which is what figure 3 concludes. Similar analysis was done on the ranking of max responses, and we identified 9 more compounds in figure 3. Moreover, we were able to see that the ranking is highly uncertain, which is undetectable when ordering single-point estimates, as in figure 3. A second commonly asked question when we do compound selection is how many or which compounds are better than a given compound C? Again, this is commonly done by ordering compound metrics and selecting those that meet our selection criteria, which is often related to a compound of interest. Using this approach in figure 5, we identified 8 compounds that are seemingly more potent than compound X, 10 compounds more efficient than compound X, and 4 compounds that have a better IC50 and max responses than compound X. This type of selection is not based on statistical comparison, and thus we propose to incorporate the notion of statistical significance in the selection by answering a more general question. for which pairs of compounds can we statistically confirm superiority for a given alpha threshold. We construct a directed acyclic graph, a DAG, to illustrate relationships amongst a set of n compounds. Each possible pair of compound is compared with our two compounds comparison methodology. If the comparison is significant, then an edge is added to the DAG, and redundant edges are eventually removed by transitive reduction. The DAG in figure 6a gives us a global picture of compounds' potencies, and we see that there are 8 compounds that are significantly more potent than compound X. We can also see that compound X is itself more potent than 11 compounds. In this specific instance, if there exists a path from node I to node J, then the IC50 of I is significantly smaller than the IC50 of J. In figure 6b, we have a simplified DAG with only the compounds that are significantly more efficient than compound X. And finally, in figure 6c, we have another simplified DAG representing this single compound having a significantly smaller IC50 and a larger max response than that of compound X. The two last results are quite different from the one obtained in figure 5, suggesting that the conclusions from that figure are mostly insignificant. The two approaches presented here facilitate compound selection. They help the experimenter identify the compounds that are most likely the best amongst a set and which are significantly better than a given compound. The method outperforms commonly used approaches and can help lower experimental costs. Finally, both approaches can be paired and used with various selection criteria. Thank you for your interest in our work and have a wonderful day.